Hey, welcome back to the StackIt series. In the last video, we did some profiling and actually sped up our algorithm by quite some amount. We also discussed why re-implementing the board in NumPy might not be the best idea, even though I thought it should actually speed up stuff a lot. It made it much slower. And in this video, we're gonna start a couple of videos on how to implement AlphaGoZero in StackIt. So we could call it StackIt Zero or something. And disclaimer, I've read a couple of things on AlphaGoZero and how it's implemented, and I briefly skimmed the original paper. I guess initially in this series we will implement what I understood how AlphaGoZero works, and then keep digging until we converge to how DeepMind implemented it, and then hopefully train a network which will beat our alpha beta search by a big margin. We should actually run another game of Monte Carlo tree search versus alpha beta with the new board. Now both algorithms can search deeper, I think. This might make another interesting game. But today we finally start with the deep learning. Initially, I want to briefly explain how does AlphaGoZero work. So I want to use this AlphaGo Zero cheat sheet, which is from this Medium blog post. I at least think this is the original author. If not, then I'm sorry. We might actually dig into what's the difference between mu0 and AlphaGoZero, but for now I will just kind of follow also what he wrote in his blog post about how to implement this. And he has this cheat sheet, which I'm now going to use for explaining how it works. So in principle, AlphaGo Zero is Monte Carlo tree search combined with a neural network. Let's first talk about these two things. So Monte Carlo tree search we have already implemented for StackIt. Just to briefly recap how it works. Initially, you start with an empty tree or just with the root node. You pick one of the next moves at random. You add this next node into the tree, and then you play the game until the end without adding any further nodes. Then you check who won at the end of this game, and then you backpropagate the results up to the root node by saying how often has this position been played and how often did the current player win in this position. And then you start another simulation where you might choose another node at random. Then you do a playout. Maybe you choose the same node at random. Then you add one deeper step node, and then you play at random. And you do this as much as you can in the time that you have, trying to collect a good statistic at how well does this node do. I think we can see something like this here. So in this particular board position, the move 3-0, which is here, has been played 13,000 times, and the win rate is 51%. These simulations, at least in my implementation currently, is just purely random moves. For various games, you might have other heuristics on which moves you might want to play more often. Okay, and another thing that you can add on top of that is the upper confidence bounds. Also a heuristic that if you have already added all possible moves of a certain depth into your tree, you want to maybe play nodes that have a higher win rate a little bit more often than you want to play nodes that have a lower win rate, just to make sure that you explore more promising nodes better than you explore less promising. As you can see, we also have this implemented here. The move 1-1 only resulted in a win 35% of the time, so overall it was only played 500 times out of these 50,000 games that the algorithm played. There's one caveat here. While I think usually in Monte Carlo tree search, you play the game until the end. I limited the maximum depth here to 10 because I thought having a higher statistic, like a higher number of played games, especially against a human, is much better than having few games played but very deep. In this case, our algorithm thinks that 51% of the time after 10 moves, I have more stacks than you do. So this is a parameter. We can tune this. Yeah, back to AlphaZero. The way how this changes in AlphaZero is we now have a neural network which will tell us the probability distribution of the chance of winning by taking a certain move. So one of the outputs of the neural net is for each possible field, how likely am I going to win when I take this move? Then during the training phase, we will use the distribution to randomly draw. This already means if the network thinks that one move is more promising, we're going to draw it more often than other moves. And then the second change here is we do not run a simulation all the way to the end to play the game. We just check, and this is the second output of the network, at the last node that we expanded, we check how likely are we going to win in the current position. So our network will have two outputs, one output which is called value head and one output which is called policy head. The policy is basically the same shape as our board, and it will tell us for every move how likely are we going to win. And the second head is going to tell us in the current position that we are at, how likely is the current player going to win. Yeah, and instead of then using the real simulation all the way to the end, we just ask the network at the last step, hey, how likely am I going to win? And then we backpropagate this. In case you were reading this while I was talking, I think mostly the stuff also is written here. So we choose the action that maximizes this. And then until we reach a leaf node, then we calculate P and V, and we backpropagate that we played. So N is the number of plays, W is the number of wins, we add the probability of winning, and Q is the average win rate. Down here you can also see when we actually play in a tournament or something, we would just choose the best possible move after doing all the simulations. And in this case, the best possible is actually the one with the highest number of choices, number of plays. This comes probably because of how the distribution works. Oh yeah, and for training we run it stochastically, where we choose one of those moves according to some distribution. Okay, as for the network, DeepMind used a really deep neural network. Like, it has this input layer, which we're going to talk about in a second. Then it has one convolutional layer, and then it has 40 residual layers, and then it has the two outputs, where the two outputs themselves also contain some convolution, batch, normalization, and then the policy head. This was the value head, and this the convolutional layer, and this the policy head. Similar, and this is how the residual layer looks like. I think for our StackIt, we're not going to need this big of a network, so we're going to start with something much smaller and see how far we can get. The input to this neural network in case of Go was this 19 by 19 by 17 stack. So a Go board is 19 by 19 fields, and then they have 17 different features where they have one feature map just for the black stones, one for the white stones. They have the 7 previous moves. So while on this board we would see the last move that black made, on this one you would see the previous move that black made, and then the previous, and so on and so forth. And then the bottom layer is just a matrix that has either all ones or zeros, depending on whether black or white plays. For our purpose, we will probably either also have 2, 3, 4 layers, something like this. So we're also going to have one layer, which is our board, maybe only with the green stones, only with the red stones, or boxes, or stacks, or whatever you want to call it, and one additional layer according to whose turn it is. How does the training pipeline look like? And this is what we're going to implement now. So first off, we need to somehow change our Monte Carlo tree search to incorporate a neural network. We're going to just, I think, start with copying the code that we have and then just put a network inside. And then next we need to start this pipeline. So we're going to have some self-play happening, which is a randomly initialized network starts playing against itself. Oops, sorry. And then for each move, we store the following information. We need to store the feature in the network used. We need to store the probabilities that we have from the Monte Carlo tree search. And we need to store whether the game was won or lost by the player. For training, they have some loop where some workers, I mean, all of this was distributed, right? We're going to have this synchronous for now. So we have some, how's it called? Some memory of past seen games. So they store the last 500,000 games, and they sample 2048 positions from that. It's a bit unclear here if games actually means this is like one game can have up to 200 moves in Go, so this would actually be a huge number of positions. But anyway, we're going to have some form of memory. We're going to randomly sample for this. They're going to retrain the neural network. And the loss function is predicting comparing the predictions of the neural network and the search probabilities and the actual winner. So for the policy head, we're going to compare it to the probabilities that Monte Carlo tree search gave us. And for the value head, we're going to compare to the actual winner at the end of the game. And then we have some regularization. This is kind of interesting. Thinking about the other deep reinforcement learning series that I started, I would have assumed that for the policy head, they just take whichever move was actually taken and leave the rest of P the same. Okay, so one step back. How it's done if you want to, for example, train a spaceship that flies through space and collects resources, as we do in the other tutorial. You take the output of the network, which would be P, then you take the action that was actually taken in the game, and you see what was the reward you got for this action while playing the game. In this case, the reward for this action would be either a win or a loss. So you leave the whole matrix, so the probability for each of the moves the same, except for the move that was actually taken, and you somehow increase the probability of this or decrease the probability of this. So this is interesting, but since they take the cross entropy loss, which is kind of a categorical like a softmax layer, you know, it should add up to 1 and everything. This may be hard to implement. Anyway, so there's some workers which self-playing all the time, and then there's some workers which keep training the network all the time, and then there's some workers which evaluate the network. They want to test and see if the new network that is trained by these workers is actually better than the current network. And what they do is they play 400 games between the latest neural network and the current best. And yeah, both players use the Monte Carlo tree search, and then if the latest network wins 55% of the games against the old network, then they replace the old network. Yeah, this is about it. This was pretty dense. I hope I could get the point across. I think implementation-wise, this is gonna be more or less simple. There is details in the paper that I might have to look up where if you self-play, I remember something like, I think, and I'm not sure, like how much time do you give the algorithm to search? I think what they actually did is they only did one play out or something. Select a move after 1,600. Yeah, I need to first run the. I need to read this a bit closer because it seems that they have these 1,600 simulations where they select the moves according to this, and then they have this one. Okay, you see, I still need to read up on this a little bit. I didn't have too much time recently. Yeah, and then how much time, thinking time do we give the network here? I think at least somewhere I read they just take the most likely move all the time and then just very quickly iterate through full games instead of spending much time searching. But this would not work with this one, so I'm not sure. This part is kind of clear. I mean, I have to figure out how in Keras you can build your custom loss like this. It's probably easy, but let's see. And then evaluating the network, yeah, we do this all in much smaller scale. Unfortunately, I'm not quite sure. This video already got quite long. With 17 minutes, if we start coding now, we're barely gonna do anything. I wonder if I just make a separate video. So this is going to be the introduction for the deep learning part of the StackIt series. I hope I could kind of make clear how AlphaGo Zero works in detail, and then in the next episode we're going to start the implementation. And since this is kind of important to me, I might just go ahead and implement it before I do the video so that it doesn't get too confusing. And then I will re-implement it on video, but I will do it before. Anyway, thanks for listening and bye.